Anna Gülcher speaking with us from ETH about the work actually she has done when she was in her master's research. Well, currently she's pursuing her PhD degree in ETH. So with that, I'll give the rest down for Anna. So this is like semi-formal, so we are not that strict uh, in
That's
terms
okay.
of the dressing, etc. I only saw one speaker that dressed up, but I think it's okay. I think totally fine people that don't need to dress up for this talk. And so with that, I'll give the rest up to you. And normally we have 45 minutes for the talk, another 15 to 20 minutes for interaction with the audience. Okay, there we go.
That sounds good. All right, so I'm going to share my screen. Just a minute and put it full screen. Are you? Yes. Are you seeing my screen? Just to check. If not, you can speak up. Okay, perfect.
Yeah, the voice is clear. Okay, go ahead.
All right. So hi everyone, welcome to this seminar. Glad that you can join me in your evening time. And I also want to really express my gratitude to be approached for giving this talk. So my title of my talk is called Corona Structures Driven by Plume Lithosphere Interactions and Evidence for Ongoing Plume Activity on Venus. So this is a mouthful, but I hope through the course of my talk you'll understand in more detail what I mean by all of these terms. So this research, as was mentioned, started quite a while ago while I was a master's student working at ETH. My supervisors of my master's project were Professor Taras Giria, who is a professor at ETH Zurich, and Laurent Montesi is a professor at the University of Maryland. He also greatly contributed to this work. And then there's a postdoc, Jessica Munch, who also helped me with numerical modeling design. So this work would not have been the same without them. It has been my master thesis, but because of we were very interested in the topic, I continue with this work a little bit during the last year or so of my PhD. So okay, so everything that I will present with this talk today has been published last year in this Journal of Nature Geoscience. It's in summer, I believe, in July 2020. And I've also written an outreach post for the nature astronomy community. So if after this talk you would like to read further, I can recommend these two articles to get some more information about the science. So my seminar today will be about, we'll go along three main themes that I've listed above. So I will first introduce some history about how we explored Venus and what we came to know about the planet and what is so puzzling about the planet. And I'll further introduce these mysterious corona structures, of which images are shown here. Then I will talk about our 3D numerical modeling study, with which we assess the formation of these corona structures, and I will present the main highlights of the study and what causes the differences in these structures that we see. And finally, I will guide you through how we used our numerical modeling results to map out ongoing plume activity on the planet by individually assessing these structures at the surface from observations from planetary missions. So this is a schematic image of our solar system, with our world being here, and Venus is our neighboring planet, which is a bit closer to the sun. And Venus received a lot of attention of space exploration several decades ago, and this started around the 1960s and 70s already. And in fact, Venus was, in these early years, the most popular planet to investigate other than Earth. So an overview of the main missions to the planet are illustrated here on the right. The Soviet Union was actually the first country to extensively attempt to get spacecraft to Venus with their Venera missions. And Venera means Venus in Russian. There were about 16 missions with launch windows every 1 to 2 years in this time period. And out of them, 10 successfully landed on the surface of the planet. However, due to the extreme conditions on the planet, with which I mean very high surface temperatures and pressures, these probes could only survive for very short amounts of time before being destroyed. So the very first missions to attempt to Venus is the Venera one, and this spacecraft is shown here, and I'm always quite fascinated by the looks of these very old spacecraft. The launch of the spacecraft to space was successful, but when it was flying past Venus, the contact was lost, and this resulted in no returning of any data. And scientists said that the mission likely failed to overheating of the sensors. The first successful landing on Venus was by Venera 7, and this happened right now over 50 years ago already, in December 1970. And this machine landed on the Venusian surface, and it remained in contact with Earth for 20 minutes as it tried to survive the high temperatures of almost 500 Celsius degrees. And just as an illustration, the atmospheric pressure on Venus is about 19 times that of Earth, which would feel as if you were swimming 900 meters underwater. So the very first image came from the Venera 9 and the Venera 10, and these are shown here. And basically what you see, the image of the surface shows a smooth surface with several blocks distributed. So one of the most successful Venera missions was the Venera 13, which is shown here. And this craft on the left was the lander. And this spacecraft sent the first color image of the Venusian surface and analyzed soil samples. So the probe operated for more than 2 hours, which is very long considering the planet's hostile surface, and it was really considered a huge success. So a few more spacecrafts follow since 1981, but actually since 1984, there have not been any landers on the planet anymore. And this image is returned by this spacecraft is shown here. And this is a colorized image. And the images reveal very smooth plains, and the soil analysis indicated that these plains are basaltic in composition, which is similar to the oceanic crust we have here on Earth. So then in the 90s, there was a very successful mission called the Magellan mission, operated by NASA. And this remains up to today one of the most important missions, as it provided a near global data set of imagery, altimetry, so topography, and radiometry. Over 98% of the surface was mapped, and these maps resulted in a burst of scientific studies following this mission regarding the surface and interior dynamics of the planet. So since the Magellan, the terrestrial science exploration has been less focused on Venus, but more, for example, focused on Mars. And there have only been 2 relatively recent missions to Venus, the Venus Express by the European Space Agency and the Akatsuki mission from Japan, the Japanese scientists. Although the main objectives here are to study the Venusian climate and atmosphere. So for us geodynamicists, the Magellan mission data remains most fruitful up to present day. So I will talk a little bit about what data of these various missions revealed. And the first thing that they revealed is that in many ways, Earth and Venus are very similar. They are often called twin planets, since they have a similar size, a similar mass, a similar Brock composition, internal structure, and gravity values. Yet there are also profound differences between the two, of which I have listed a few here. So in comparison with Earth, Venus has a very hot surface temperatures. It has a very dry interior. There is likely no water anymore. And there is no apparent mosaic of moving plates on its surface, like the Earth does in the form of plate tectonics. So Venus is often proposed to be a model case for the early Earth, when the Earth was much hotter and when plate tectonics did not yet operate on our planet. So studying Venus could reveal also a lot about the history of our own planet. And one of the most striking observations on Venus, at least in my point of view, comes from the number and distribution of impact craters on its surface. And this is shown here on the left. There are relatively little impact craters on the Venusian surface in comparison with other planetary bodies. which could suggest that the surface age is relatively young. And moreover, their spatial distribution cannot be distinguished from a random distribution. And this is often interpreted that the Venusian surface is apparent young and uniform in terms of surface age, an estimator of only a few 100 million years old. So this is in strong contrast with the Earth, where we have highly variable crustal ages of several billion years of old to several thousand years old. And originally, the young and uniform surface age of Venus has been ascribed to a global catastrophic resurfacing event about 500 million years ago. And this suggests that at this moment, after such a global activity that resurfaced the whole globe, the planet has been mostly inactive or geologically dead. However, more recent research shows that equilibrium processing may also explain the crater distribution on Venus. And this suggests that there is ongoing regional resurfacing constantly going on. So let's focus a little bit more on the Venusian surface. So sample analysis, as I said, indicated that the surface is mostly basalt-like. And despite the absence of a global network of moving plates, the Venusian surface is littered with many volcanic and tectonic structures. So the abundance of these many structures is quite evident in this mosaic image made by the Magellan mission. And as you can see, the surface of Venus, the colors here indicate the topography. The surface of Venus hosts some highlands that are shown in red. But you also see many, many structures in various shapes, formats, and geometries. And these structures are commonly attributed to underlying mantle convective processes because the surface strains and displacements are very modest. So a glimpse of these structures are shown here. And on these radar images, I just illustrate a few of the structures that are very abundant on the surface. So we have these kind of pancake domes that are a little bit flat, flat domes of only 10 kilometers long, but you also have many mountainous terrains like these ones here on the right. You see various rift valleys, volcanoes of different sizes and sorts, but also nova and corona structures, to which I will get back to in just a minute. And these two structures here are unlike any that we have seen on Earth. So exactly to what extent all of these structures reflect the current state of the planet's interior and whether Venus is geologically active today remain the key questions that I'm trying to assess with you today. So this goes back to the two main lines of thought that are out there regarding the Venus global tectonic regime. So we have this catastrophic resurfacing event that likely happened a few hundreds of million years ago, or there could be equilibrium resurfacing processes going on. Well, this upper hypothesis was very well accepted when it was first proposed in the 1990s. And this really indicates that at present, Venus is geologically dead and there is not much going on. However, there has been some exciting research in the last few years, all with various techniques that propose that there are individual sites of present-day magmatism or volcanism on the planet. And this all points towards Venus being more geologically active than originally thought. So what we do with our research, we basically build up on this line of thought by proposing that these mysterious corona structures bear testimony for turbulent processes of Venus's interior. So what are corona? Corona are these circular or crown-like volcanotectonic features, and they are abundant on the surface of Venus. And here there are 3 examples of these structures with radar imagery. So there are over several hundreds of them all over the surface. I believe the count as of today is about 500. And they are all associated with this radial and concentric faulting patterns. They all are associated with volcanism and tectonism in these circular patches. So their sizes really vary a lot. They are some of them are relatively small, from just about 100 kilometer wide, but some of them can be over 1,000 kilometer wide. And I just want to emphasize that these structures are really big. So for example, this is the country of Switzerland, where I currently live in. And the corona that is shown here, the Aramaiti corona, has a diameter over 400 kilometers. And this is larger than the whole country that I live in. So these are not small circular patches. They're actually huge structures, all distributed all over the Venusian surface. The last thing I would like to point out that the morphologies of these corona structures can all differ individually. So this is a study that has been done already over 20 years ago that summarized the various topographic profiles that are displayed by these circular corona on Venus. So some corona are very simple. They exhibit like these domes or plateaus kind of structures, but many of them are more complicated. They have certain rises, certain valleys, and have multiple structures going on within this whole region. So how are they formed? Well, usually they are understood to form above upwelling mantle plumes, hence the circular patches. And they are thought to form by the crustal stresses that develop above these upwelling mantle plumes, possibly followed by relaxation. Some corona have been identified to feature structures that could be suggestive of ongoing subduction or lithospheric delamination that happens on the circular margins. And in our paper, we discussed that for the formation of corona, these plume lithosphere interactions models are indeed dominate in the hypothesis in being able to explain key features of corona, such as the topography, the faulting, and the magmatism. However, previous numerical work on plume lithosphere interactions was quite limited. This could be in terms of the dimensions investigated or the numerical implementations of magmatism and volcanism. And they also very often just focus on one type of corona structures, while we see many different types of features and topographies. So in our study, we use sophisticated models of plume lithosphere interactions in 3 dimensions to assess the formation of large corona on Venus and the reason behind their morphological diversity. So this brings me to the numerical study that we've done. So we have employed 3-dimensional models with which we use a thermomechanical code called I3-Elvis. And I would only like to briefly mention a few specifics here. So this is a 3D geodynamic code that uses the finite difference method applied on a staggered grid and a marker in-cell technique. It solves for the conservation of mass and momentum and energy, like most geodynamic codes do. But melting of material and crustal accretion and phase changes are all implemented in a rather simplified manner. And lastly, the model that we employ assumes a viscoplastic rheology. And this rheology includes strain weakening of the angle of internal friction of rocks, and also local melt-induced weakening of lithospheric rock. And if you want to know more about these techniques, you can see the method section in our paper or ask a question at the end of this talk. So the numerical model setup is here shown on the right side. We basically place a buoyant thermal mantle plume, which is shown in this orange field in the composition space, beneath a warm basaltic crust, which is shown in green colors, under Venusian temperature conditions. The modeled box is quite large, approximately 2,000 by 2,000 by 400 kilometers, and it is resolved by over 250 million markers. And we have run 21 numerical models. And these models vary in their initial model setup in 2 main aspects. Basically, we varied the plume buoyancy or the lithospheric configuration. And the plume buoyancy is affected by the plume temperature or its size. And the lithospheric configuration, we mean by that the lithospheric strength or the temperature profile of the lithosphere, but also the crustal thickness. And we all chose values that are considered appropriate for Venus, coming out of other studies on Venusian geodynamics. So I will now show the evolution of our reference model. And this is the first time step that I'd like you to see. So basically what we see here is a cross-section in the middle of the model with the composition field. And on top you have the surface view of the topography that is above these structures. And high topographies are shown in red, while deep negative topographies are shown in blue. So basically, soon after the onset of model evolution in our reference model, the buoyant mantle plume rises and is buoyant enough to break through the lithosphere. It breaks up the crust as well, and it forms these, it pushes the lithosphere across the side. So the newly formed crust is barely visible, but is here shown in crust in pink and purple colors. And the surface topography at this stage is characterized by an elevated interior, shown in red, surrounded by a deep circular trench. So as time passes, the plume head widens and pushes the lithospheric material outwards and downwards. And at the plume margins, you have the weak lithosphere that repeatedly drips into the mantle, as is seen here. The surface topography here is characterized by, again, a deep trench at the outer margins of the corona that is situated right above the downwelling material. This surrounds an interior high that slowly loses its elevation through time. And finally, after enough time has passed, the plume has cooled down and recrystallized. The surface topography here is characterized by an outer elevated rim, which surrounds the region where material has broken off in the lithosphere. And the interior here, the surface topography from the interior is here now depressed, which is overlying the region where the new crustal material is very thin. And this is in clear contrast with the topographic profiles we've seen before. So I'm now going to show you the video of this specific model in temporal evolution, so you can have more of an intuition of how the plume dynamics and the corona shapes at the surface change over time. So important to note is that in this video, the time steps keep increasing as the movie progresses, so the temporal intuition may not be completely correct. But I will show this movie anyway to make you have a sense of what's really happening. I will show the short movie 2 times, and I would recommend the first time to have a look at what's happening with the composition fields and what's happening with the plume and the crust. And the second time, have a look at the topography at the surface. So I will, if I can, run the video. I will start now, so have a look at the compositional field. All right, and then I will replay the video, and I will encourage you to have a look at the surface field in terms of topography. All right, so this was our reference model, but we've of course analyzed a lot of different models. So I will show a few other models that display slightly different behavior. So our next model is a model in which the lithosphere is made a bit stronger, but it could also occur when we have a thinner crust. So we look again at 3 snapshots of 3 different times of model evolution. And basically on the left, you see that again, our plume rises and is buoyant enough to break the lithosphere and pushes the material aside. And in the middle, you see that as the plume widens, the rigid lithosphere at the plume margins forms this retreating circular subducting slab that eventually breaks off. And that happens here on the left side of this model and almost on the right side as well. And this actually forms a short-lived episode of retreating subduction at the corona margins. And similar to the previous model, after a long time, the plume has cooled down and the surface topography is completely inverted into the opposite in terms of topography, with an outer rim surrounding an interior light depression. And then finally, the last model that I'd like to show is one that is completely different. This is the case when we initialize a very weak plume, and by this I mean that the excess temperature is relatively less than the other models, or a strong lithosphere in combination with the weak plume. And this you can see here. Basically, in these models, the plume is not buoyant enough to break the lithosphere and rise up to the surface. Instead, it spreads laterally underneath the lithosphere and subsequently cools down. And the surface topography is throughout the model evolution relatively equal, as it is marked by an elevated plateau. And also as the plume cools, this surface topography does not change significantly. So we really detected these very different behaviors and types of plume lithosphere interactions in our corona models. And this strongly depends on two factors in our numerical study. And this will be plotted in this graph. So the vertical axis here marks the buoyancy ratio. And this is basically the ratio of plume buoyancy over lithospheric strength. And the formula that we've used is written here below. Basically what this means is that models with a very strong or hot big plume or a very weak lithosphere plot at the top of the graph. And plumes are here more able to break up the crust. And in contrast, models with a very weak plume or a strong lithosphere plot at the bottom of the graph. And the horizontal axis is called the skilled crustal thickness, but it is also represented by the Moho temperature. And this value depends on the thickness of the crust over the thickness of the thermal lithosphere. And what this indicates is that on the left of the graph, models plot which have a thin crust or a very strong lithosphere. And on the right side of the graph, models plot with a thick warm crust or a thin and weak lithosphere. So in this image, you see all of our numerical models plotted as circles, and all the colors mark different types of plume lithosphere interactions that we've identified. And they clearly plot in different parts of this graph. So on the top right corner, models display a buoyant mantle plume that fully penetrates the lithosphere, with the lithospheric dripping happening at the margin. And this is similar to the first model that I've shown you. Then on the top left corner, models display also buoyant mantle plumes that again fully break up the lithosphere. But instead of lithospheric dripping, here we have a retreating subduction zone of the more rigid crust, but eventually the crust and lithosphere is not strong enough to maintain the subduction zone, and the slab breaks off. So I really want to emphasize that in all of these models in this subduction regime, the retreating circular subduction episode is always followed by breakoff, and there may be several episodes of retreating subduction and slab breakoff. Then for very strong plates or weak plumes, the plume is not able to reach the lithosphere and instead spreads laterally underneath it, like the last model we have seen. And then finally, we also identified this kind of transient regime shown as the kind of red colors plotting in the bottom right of the graph. And here the plume partially reaches the crust and partially breaks it up, but it's really a sort of in-between behavior between all of these regimes that we've seen before. More details regarding these plume lithosphere interactions can be found in our paper. And what's very interesting is that several of these types of plume lithosphere interaction may really help our understanding of plume lithosphere dynamics happening on early Earth before the self-consisting plate tectonics operated on our planet. So the outcome that I'd really like to focus is on the topographic evolution of these top two regimes. And here I'm showing two plots that show the temporal evolution of topography for these two models that we've looked at before. Basically, the vertical axis in these graphs represent the radial position of the corona, with 0 being right in the center of the corona. And the horizontal axis marks the time. And you see basically the average topographic profile changing through time for the millions of years that we've modeled. So I also added some snapshots that show the early and the late phase of plume lithosphere dynamics. And what you can clearly see in these two images of topography over time is that the crustal variations induced by the plume lead to a completely isostatic response during which the topography profile completely inverts to the opposite profile from the early stage to the active stage of the plume, the early stage to the inactive stage or late stage of the plume lithosphere interactions. So, and I've summarized that even in more detail in this figure. So basically what was first this interior high surrounded by a deep trench that marked the ongoing plume lithosphere interactions is afterwards followed by the complete opposite with an outside high rim surrounding an interior deep depression. And basically what this indicates is that there is a clear topographic inversion happening from an active stage to a completely inactive stage in terms of plume lithosphere interactions. So the key points of this numerical study are the following. We found that the morphology of the corona is directly related to what processes are going on underneath it. And most importantly, the crustal thickness variations eventually lead to an isostasy-driven topographic inversion from a circular trench surrounding an interior high towards an outer rim surrounding an interior depression. And what this kind of indicates is that the topographic pattern of corona may be indicative for the activity of the plume underneath. So this was basically the end of my master thesis project. But after discussions with my collaborators and with other scientists, we really found this outcome very excited and we wanted to move forward with this. And after some fruitful discussions, we had an idea of how we could use this information to say something about Venus. And the question that we would like, the task that we went forward with is that we wanted to address the current state of plume activity distribution on Venus by looking at the large corona structures. So that was the second part of our study. And basically what we did here is we evaluated the possibility of present-day plume activity on Venus by looking at the surface topography of the 133 largest corona on the planet. So the topography data set comes from the Magellan mission from several tens of years ago. And we used the USGS Corona database to provide more information on their geometries, on their locations, and on their names. And so we classified plume activity based on our previous numerical results. And what I mean by that is that we labeled a corona as being currently active if it features a clear outer rise and a trench that indicate ongoing activity on the plume margin. And we label the corona inactive if it shows the complete opposite, if the topographic profile showed a clear outer rim and an inner depression. Many corona were also classified as unknown because many features are actually quite ambiguous on the planet. Nevertheless, we did such an analysis for, as I said, over 100 corona distributed over the planet, and I will show some examples of these 3 corona. So, as an example, this is the Thur corona, and here you see the radar image, and here you see the topographic data from the Magellan mission plotted as well. So this corona really features this clear outer high surrounding an inner depression, and features that, according to us, mark fossil corona stages above a fully crystallized plume. Then in contrast, we have here the Alamaiti corona that I've also talked a little bit about earlier in my talk. And this corona really features a lot more structures, as you can see in terms of topography. So it clearly has this kind of outer rise surrounding an inner trench. And this kind of implies to us that there is evidence for lithospheric bending and suction above downgoing lithosphere And the corona, in our point of view, is currently in an active state that predates the final complete topographic inversion. Then another corona that I would just briefly like to show is the Artemis corona. And this is a very interesting feature on its own. This is the largest corona on the planet. The diameter of this structure is over 2,000 kilometers wide, which is like larger than whole of Europe, likely. And there are many structures seen, but on the southeastern side, that's the part I want to focus on. You have this clear trench surrounding an interior high, and also there is this outer rise behind it. And this is just kind of a sort of comparison with one of our models that we were able to reproduce some of these key structures seen on this southeastern edge of the corona in our numerical models, which is quite promising. But in any case, this topographic profile to us indicates that this southeastern margin of the Artemis corona is still undergoing tectonic and magnetic activity, which is in line with other research that indicated or suggested that there is retreating subduction happening on this margin of the corona in this southeastern part. So we did such an analysis individually for over 100 corona, which was quite time consuming, but it led to the following outcome. Basically, we identified 37 corona that express structures consistent with ongoing plume activity. And they are shown here as the red dots. Most of these corona are clustered in the Themis region and the Laterra region, and some of them are also here in the northern hemisphere or along the southern margin of the Aphrodite Terra. 35 other corona were classified as inactive, and they are shown as the white dots. And the full database of this analysis, including details of every individual corona, also the ones that we were not able to classify, is made freely available online. So these results really present new evidence for recent tectonic and magnetic activity on Venus, and this complements previous indications of other studies of such activity on the planet. So the key points here is, again, the 3D numerical study that we explored indicated that the morphology of corona is related to what processes are going on underneath it, and the topographic patterns could be indicative for plume activity. And this led us to identify 37 corona whose structures are consistent with ongoing plume activity. And most excitingly, this provides new evidence for widespread plume activity on the Venus. And this indicates that this planet is not so geologically dead or resting after all. So what to go forward with this? So in my point of view, future studies should really explore how this global distribution of upwelling mantle plumes reflects the circulation pattern of the deep interior. I'm really interested in this aspect also because I'm currently working on mantle convection inside planets. But obviously we have only used topography for our corona activity classification, and a more thorough study is also needed to compare with other data sets, such as gravity or geology, by looking at the imagery, and also finding perhaps Earth analogs or investigating early Earth tectonics before plate tectonics on our planet is also of very high interest to me. I mainly hope that this research, we have drawn attention to a hotspot Venus, and luckily there have been quite some other exciting recent publications also drawing planetary science attention back to Venus. And to quote one of the recent outreach blogs that we've written, is that it appears that Venus is slow to reveal its secret. Has our twin planet been misunderstood all of this time? And then finally, although existing data from previous missions remain highly valued, the last geodynamic study of the Venusian surface took place over 25 years ago with NASA's Magellan mission. And this is hence very outdated. The data that we have is very limited, and especially in terms of resolution. For example, the topography data set that we have to use has a horizontal resolution of 10 to 25 kilometers. And this really precluded us to look at smaller, relatively smaller structures on the planet because they are just not imaged by this data set correctly. And it also really precludes any detailed analysis of other topographic structures or to really compare with what we see on Earth. And to quote another part of the blog, it is clear that there are tremendous gaps in our knowledge that can only be fulfilled with new investigations of our sister world. So key questions that we should try to answer in the future of Venus science is, did Venus have a past epoch of habitability? What are the physical mechanisms responsible for Venus's geologic activity? And how have Earth and Venus diverged down such different geologic paths, making Earth a planet that could host life and Venus not? So only new missions to Venus can really help us address these questions. And there are 2 missions that I know of currently on the drawing board for both ESA and NASA. And personally, I really hope that these mission plans will be chosen so we can address these important scientific questions related to planetary sciences. So by that, I would like to bring you to the end of my talk. I have some references here if you wish, and I will be very open to answer questions you may have. Thanks.
Okay, thank you very much, Anna, for the science as well as for the presentation. Now it's time for question from the audience. So before us ask a question, please let us know your name and your institution. So Timo, please go ahead.
Hello, Anna. This is Mengtian.
Hi.
I think we met at Geophysical Fluid Dynamics seminar of Paul Teckley's group, right? I'm from
That's very true, yeah. Yeah,
so,
that's true, cool.
Yeah. I'm half geodynamist and half thermodynamist or petrological thermodynamist.
Oh, great.
So I have 3 questions, if time allows. The first one is about the code. The code is finite volume code, right, on the staggered grid.
Finite differences, but
yes,
that's highly related.
Yeah, those codes are mostly suitable for rectangular geometry. But in your model, you very carefully or deliberately consider the topography of the model, for which the finite difference model is not or even bad at, right? So is the topography simulation benchmarked? I mean, ideally, a finite element model would be suitable for doing deforming geometries, but
I
just
will
don't.
actually just go back to sharing. So wait, how could this is, sorry, I will stop the presenter view so I can just go back to the, so yeah, that's a very good question. So basically, we have not benchmarked, I will go back, for example, to this slide. We have not benchmarked our models ourselves. But basically what is considered to be a good approximation to include in these finite difference models is the sticky air layer on top.
I see.
This is not as accurate, I agree. The finite element method is likely better to really distinguish the actual solid surface from what's above it, but there have been many papers kind of benchmarking that and suggesting or showing that the sticky air method is appropriate on first order very much for a lot of structures. So we did not do this in our own study, but however, this specific setup has been used in previous studies, also by, for example, co-authored by Professor Tagasgelia for Earth plume lithosphere interactions. And I think in one of his 2015 Nature paper that was about start of plate tectonics by plume lithosphere interaction. There in the supplementary methods, they did the benchmark more
I see.
about this. But I agree, we did not double check this. We just
I mean,
adjust this
no
to
worries.
Venusian parameters.
It's just my curiosity. I'm wondering what kind of novel techniques can be used to implement topography, find a difference model. But I also see that Boris Kos is on the co-author list, right? And he's an expert on finite element.
Well, not in this paper, but he has been a co-author on this previous paper that I was just talking about. So he has been somehow involved.
Yes, so he has expertise in finite element. So I guess he will have a quality control of the code. So I trust your result, no worries.
Well, it could be more accurate in terms of finite element. I do agree there. Yeah.
Yes. So that's good. Another question is, I don't have the answer, and I'm very curious about the buoyancy, the result of a buoyancy ratio or something. As far as I can understand, the buoyancy will have two effects. The first is mechanical, right? Because it's a buoyancy force. So the larger the buoyancy, the larger the force the plume will impact on the lithosphere. So this is a mechanical effect. On the other hand, the plume will also have a thermal effect, right? It is abnormally hot. So when it impinges on the lithosphere, it will heat the lithosphere. And you mentioned that in your rheology model, there is melt weakening mechanism. So the heating, the melting, and the weakening will also induce deformation. But this is purely thermal, eventually thermal effect. So in this kind of ratio, I'm curious about, is there any way to distinguish the mechanical from the thermal effect? Or in your result, which effect is the major one?
Yes, that's a very good question. I have not been actively thinking about how to, in our results, quantify the different contributions. But this is very, very, very interesting. But what I would say, what seems to be most dominant in our models. So again, I may not have highlighted this very much, but Venusian temperature conditions means that the surface temperature is 500 degrees Celsius. So most of what we see is viscous behavior, or close to viscous behavior, because even the surface that we have is not like on Earth, a very cold, rigid crust. We actually have, like, by its own, the surface is relatively weak to what we're kind of used to and seeing what we see structure-wise on Earth. So I believe that the thermal contrast is very important in terms of weakening of the lithosphere, but that this drive up, I see, okay, I've just made up my mind. So there are two things I see. Basically, first of all, the mantle plume should be able anyway to break up the lithosphere, regardless of what happens afterwards. And for that, this melt-induced weakening seems to be very important in our models. So I have also run models where this melt-induced weakening effect is less, which then contributes to the lithospheric strength. And this is really, really, really determining whether this plume can break up the lithosphere or not. And then the background temperature profile is key for what happens when the plume has broken up this lithosphere. Is the crust still on the sides so warm and weak that it will kind of drip down, or can it be sustaining a subduction episode for a short amount of time? So I have the feeling that the thermal contrasts are of most importance in our models, but I have not been able to quantify this, and I think that's a very interesting aspect. Yeah.
Thank you. I mean, I as I said before, I have no answer either. My intuitive feeling is the same as yours, because basically, you can reasoning like this, right? The thermal effect mostly affects the rheology, which is exponential dependence on temperature, right? Newtonian or non-Newtonian. But the temperature effect on buoyancy is delta rho g delta t. So that's a linear effect. So intuitively, I would guess the thermal effect might be major. And also although I said I have 3 questions, you already answered my 3rd question, which is about elasticity. Okay. And there's no elasticity in the reality, right?
No, unfortunately not, no.
I mean, it doesn't matter for this large scale, but
exactly.
Let's see.
It could affect the time scales perhaps a little bit. So we are not too conclusive with our time scales of our models, but still the overall idea I think would be maintained as well.
Yeah, I mean, for this very large scale modeling, geodynamic modeling, if you consider elasticity, then the time step of your model will be extremely small to resolve the elastic deformation.
Mm-hmm.
And additionally, if you have such small time step, and if you consider elasticity, then the faulting or the plastic deformation combined with the elasticity will create a quite different melt migration behavior, which backwardly will affect your rheology. So resolving into finer and finer timescales might bring more rich physical process or physical phenomena. But for this global scale model, I think it can be regularized. Just ignore them for the time being. I see. Good, good. Thank you.
Thank you.
Very interesting talk. Very interesting talk.
Okay, the next question is from Chen Yunfeng from Zhejiang University. Thanks you for the great talk. Just wondering how deep is the mantle plume? And is it similar to the mantle plume we have on the modern Earth?
Probably so this is a very good question, I think. Let me also just perhaps bring up a relevant slide. So I must confess, in our models, we basically look at the upper mantle only, and we place this mantle plume as already being situated or having this anomalously hot heat source in the upper mantle, like a few 100 kilometers below the depth of the below the surface. And we assume that this mantle plume, we've made it a spherical shape, but exactly where these plumes source. So, for example, this is very important for this kind of map. We cannot really say whether we believe that these mantle plumes are sourced all the way from, for example, the core mantle boundary that we see on Earth. So I'm not saying that every dot of here has to be a very hot upwelling. It can be it could be a shallow plume, because we only model shallow plumes, but of course plumes have to source from somewhere. And the most likely reason for the source of a plume must be like at greater depths, like we see on Earth, so above the core mantle boundary perhaps. But we cannot say with certainty. What I would suggest, or what I have the idea, is that if you, for example, this Themis region is really has a high cluster of these kind of active shallow structures. And also some other studies have indicated that this Themis region is a sort of hotspot due to other volcanic observations. So it's very likely that these different locations on the surface could all source from some deeper heat contribution in the deep planet that could then kind of branch up into these multiple shallow plumes at the surface. But these are kind of just speculations, and I do think that the plumes will look relatively similar as on Earth, because we have the idea, at least, that the interior structure or the mineralogy is also relatively similar. But we cannot say with our study. So that's something. I know a group of Scott King, I think, who's the scientist in America. I know a group that are trying to kind of address plume behavior on global scale and on Venus. So hopefully they will provide some more answers here.
Thank you.
Thanks.
Okay, more questions from the audience? Yeah, I just have a quick comment on
Yes.
this one that it's a wider question. That do you think that the deep interior, the command structure of Venus is homogeneous, or do you think that it might have a similarity as Earth, like with a large low shear velocity provinces, basically making the Earth command boundary quite heterogeneous itself?
That's a good question.
Yeah, because I'm thinking about this because for the Earth that you look at those plumes, then you plot them, you could try to make them at the edges as LSVPs. And here for your case, that at least they don't as randomly scatter for the for the plumes that you infer from your study. At least they are not too small scatters that are equivalent to each other, but at least they are too, let's say, concentrated into zones. I would say that. Yeah, I would like to see what you think about it.
Yeah, that's a good question. So I must admit that this kind of lining or shading is quite suggestive, but like people could interpret it differently. But we've kind of interpreted that it may be like maybe in the deep interior there is this kind of source in the southern hemisphere that creates a lot of upwelling, especially related to the northern hemisphere. And of course, on the Earth, like such a sort of our bimodal distribution of plumes or is indeed related to some heterogeneity below. Yeah, I really don't know. I think it's one of the things that is very interesting to pursue in terms of this kind of mental convective modeling of Venus. I do believe, I mean, so for Earth, the LSSVPs are thought to originate from either primordial, ancient, dense material, or perhaps recycling. And I think a recent paper, at least, suggested that the magma ocean could have been also been present in the early Venus, but this is still under consideration, and that could lead to at least primordial heterogeneity as well. I think they concluded that. So it's very likely, but again, this is kind of still being very suggestive of the planet, and a clear answer I don't have, but I think this is one of the aspects to answer about sort of plume distribution or deep mental circulation. I think the model should definitely take sometimes into account some heterogeneity as well, as these can really kind of fixate your mental convective pattern. It will be interesting to see, but I do not know. And at least I think it's not in such a high degree as on Earth, because there is not such a clear distribution as we see on Earth, but that's more my intuitive feeling. So perhaps not a very scientific answer.
I had a quick thought regarding this picture, Anna. So I'm not sure if you are familiar with the work by Shiji Zhong from Colorado in the US, a geodynamist. He is basically the developer of Sitcom S. And I think he has a proposition that there are degree 2 or degree 3 or 4 mantle convection. For example, in terms of Earth, the degree 2 mantle convection basically produced 2 huge plumes on Earth. One is near Africa, the other I forgot. But if you look at this Venus picture, it looks like if there is a degree 1 or degree 2 pattern of mantle convection that might be responsible for this distributional pattern. So it's just a quick thought. If you are interested, you should look for Shiji Zhong's paper.
Yeah, I will. Thank you very much. I think I know which paper you talk about, but I'm very bad with like exactly names. But I will definitely look it up. Thanks.
Sure. Just a quick thought.
Yeah.
Okay. The very last question from Arka from Jawadhpur University, India. It was interesting talk. I have a quick question. What would you think of this study providing further insights into the plate tectonics within Venus? Or I interpreted that, do you think that plate tectonics will occur in the future on Venus?
Ooh, yeah, that's a very interesting. So the first thing I want to say is that plate tectonics, the name is very used for what we see on Earth. And Venus definitely does not have plate tectonics because we don't see multiple separate plates with clear, distinct boundaries moving from one another. So if we say something about the Venusian tectonics, I think we have to come up with a different word or use older terms that is not plate tectonics, but maybe plume tectonics or whatever you would like to say it. But whether Venus could move into a plate tectonic regime is very, very relevant, because indeed there's suggestions that, I mean, Earth did not have plate tectonics throughout its history. It also started more hot and more kind of vertical behavior that resulted likely in surface patterns that eventually, as it cooled down, led to plate tectonics. So it is a possibility, I think, that Venus could, over a very long time scale, move towards a more Earth-like dynamics. However, I must say that because of various reasons, there are a lot of differences also happening at the, for example, at the atmosphere of Venus is very dense and surface temperature are very hot. And this has also created an effect that the surface of Venus is not cooling down as the Earth's surface does. And I think that the cooling of a planet is a major contribution into shifting to this more rigid plate tectonic style. So we cannot really say with certainty that the tectonic behavior of Venus will follow the Earth as well, but because this cooling is just much less efficient in Venus. So whether it will really get to plate tectonics, I don't know. I think our results contribute in a way that to the current understanding of Venusian tectonics, that there, in my point of view, and many others as well, there is likely some regional tectonics going on. For example, we showed that under these Venus conditions, there could be a short episode of subduction. The lithosphere is just not strong and cold enough to really create long-lived episodes of these deformation structures that really create plate boundaries. So that's what I think. Our models could help, definitely.
Okay, thank you very much again, Anna, for the talk, and thanks everybody for participating. And
thank you very much.
I personally enjoy the format of sounds like in the very first half we're in a seminar room, then in the second half people move to a bar to talk about science and to interact with each other. I think it's great. Okay, great.
I really enjoyed it.
Yeah, thank you.
All right, thank you very much. Enjoy your evening.
Have a good day. Bye bye.